Okay, so we're doing in this video question 4 and 5 from the OCR Further Maths Stats paper 2019. Question 4 is really a question apart from perhaps part C, well, definitely part C, which could appear on a single maths paper because it's hypothesis testing from a sampling of normal distribution. So it could in many ways appear that, although there is a subtlety with the central limit theorem and whether that's applied in part C, but there are principles basically that you cover in single maths too. Right, so we need to set up the hypothesis. So it's good to set up your parameters and looking at the mark scheme. They are expecting you to define what mu is. So let mu be the mean of, okay, let's look at the context, can be sorted, it's found that the mean greatest weight of the brackets, the mean of the greatest weights so do take time to get the wording right of that. Use the wording in the question that the new design will support. Okay, and then we're testing at 1%, and let's look at whether mean of the weight design can support is less than. So that means that we're doing a one-tailed test. The null hypothesis is not always involving an equality sign. So we have mu. The null hypothesis is that the mu is the same as it was for the original traditional design, and the alternative hypothesis is that the new will support less than 5, will be actually less than 500, less than the traditional design. Right, now I'm quite reassured that sometimes it's worth looking a little bit ahead of the questions, because it does say state any assumptions made in the question, because we can't really use this test unless we know the standard deviation of the actual distribution, the parent distribution of this new design, and it hasn't told us that. But with a kind of peek ahead, we can say, oh yeah, well, okay, that's what they're talking about. So part B is going to be to do with the standard deviation being the same. So we don't have to write that here because that's in the next part of the question. So our sampling distribution. So we've got a normal distribution. Obviously, the sampling distribution under the null hypothesis will have mean 500. The standard deviation, the original distribution, is 80. So we're assuming that's the same as the standard deviation of the original distribution. So the variance is 80 squared, but we've got a sample size of 40, so the sampling distribution has variance 80 squared over 40, or standard deviation, which is what we're assuming, which we'll be mentioning in the next part of the question, is 80 over the square root of 40. Okay, so now we're going to there's various ways about going about this. I do a more traditional approach, comparing to the Z distribution and using that as our test statistic. I do wonder in the years to come whether this will become a bit obsolete, but I'm still sticking with it for the time being because I think this is the most this is normally the way people do this, using the Z distribution as our test statistic. So Z is equal to our value of X bar, a particular value, take away the mean over the standard error. So that's equal to 473.0, because that's what we've actually observed, that's what we've got from our sample, take away 500 over 80 square root of 40, which is equal to minus 2.1345. Right, now the critical value, and you can get this from the formula book, but the critical value, or you can use a calculator to find it, but the critical value at 1% for Z, that's one-tailed, for Z is minus 2.326. Okay, minus 2.326. Okay, let's look at that, how we would find that on the calculator and where we find it in the formula book. Right, on the calculator first. Well, it's important to appreciate that we're actually using the inverse normal here, because we want effectively to find the value on the standard Z distribution, which is the distribution with mean 0 and standard deviation 1. We want to find the actual Z value here that leads to a 1% probability here. So we're comparing with the Z distribution and using that as our test statistic. And we've got a Z value of minus 2.1345, and we need to actually see what this Z value is for the 1% value. So if we bring up our calculator, now let's bring up the calculator. Okay, so there you go. So now the calculator, we press menu 7, and it is the inverse normal we're looking for. And the area we want is 0.01, because we want 1% towards the left. The standard deviation is 1, and the mean, we need is 0. So we're looking for the appropriate value there. And that's minus 2.326. Okay, so let's write that in. Minus 2.326 is the actual value of our Z value at 1%, which is what I've said here. But our value is our value is actually to the right of that, because it's bigger or smaller in a kind of absolute sense. So our value comes here. So it's kind of not in the critical region. So it's not significant, and we're not rejecting H0. Right, so that's how to use a calculator. It is also worth looking at the numbers in the formula book, which I'll bring up now. Well, in the formula book, we're not obviously given the negative values, but we can see the value in the opposite end of the tail here, the minus 2.3126 here at 0.99, which would be the opposite end, but by symmetry we can see that minus 2.326 is the number we're after. Okay, so that tells us that gives us that value. So we're not rejecting H0. So, but let's come to the appropriate conclusion with the reasoning. Let's modulate the answer. So we've got minus 2.1345, which is our actual value, is less than the modulus of the critical value. It's okay to do to not modulate, but then you'd have to have the inequality the other way around. So I prefer to modulate to have it consistent as if you were on the other tail. So therefore we can then say do not reject H0. There is insufficient evidence to suggest the mean weight of the new design is less than the traditional one. Right, okay, so question 9 has come up there. That's obviously not the question I'm going to do next. That'll be in a few videos down the line, so let's get rid of that. And let's go back to the question. I alluded to the answer to part B, state any assumptions. We really couldn't carry this test out. We'd have to do something called a t-test, and that wouldn't work here. Well, it's a moot point really, but we'll talk because the sample size is quite large as well. But anyway, the standard deviation is the same for the new design or the traditional one. From the traditional one. Okay. Part C is quite an interesting one, really. It was one of those ones where I thought, I mean, people have come up with different answers and still got got correct marks. I suspect the examiner had something in mind when they wrote this. My feeling was that it is not being used because we're talking about two different designs here, two different populations, if you like. And so therefore, because it hasn't said that the population of this new design is normally distributed, it hasn't explicitly said that. My feeling was that the answer was yes, the central limit is being used because we cannot assume that the population of the new design is normal. That was my feeling, so that's what I'm going to go for, and it does get the mark. So the yes, because what the central limit theorem says is even if the parent population is not normally distributed, if the sample size is sufficiently large, we can use the central limit theorem. So I'd say yes, because we should not assume population of new design is normally distributed. Now looking at the mark scheme, this is strange. You could say yes or no and still get the mark. If someone said no, because you can assume it's normally distributed, that also got the mark. In fact, it got a little bit easier because you had to explicitly say new design is normally distributed, because we are told the population of the traditional design is normally distributed. So to get that mark with answering yes, you have to say new design. Whereas if you answer no, you can say because we know the population is normally distributed. To me, I mean, we won't know unless it would be, because often the person who writes the paper is not the person who writes up the mark scheme. So without speaking to the person who actually wrote the paper, we can't be totally sure what they intended there. But what I suspect is the examiners met, they decided, they kind of amongst themselves what they thought a reasonable answer was, and they ended up deciding that both were okay, so long as that they were justified. I suspect, because I have had some experience of how these things work. Okay, right, let's look at the next question. Question 5 is a Spearman's rank question and another hypothesis test. Question 1 is to state the hypothesis. If it's Spearman's rank, because it's all about it's a non-parametric test. The OCRA are quite picky about the vocabulary you use, so you have to use the word association. So the null hypothesis is no association between orders in race. Between orders in race of this type. Of these two types. And H1, there is a positive association. Because the word positive agreement is used. Between orders. In the two races. Now for the second part, they're not actually getting us to do a hypothesis test. They're not giving us the value of RS as test statistic. They're actually tackling it the other way around and saying what value of d squared would be required to reject the null hypothesis. So I've brought up the values in the table that you're given here. Remember, it's a 5% one-tailed test, so there we go, 5% one-tailed test, and the sample size is 5, A, B, C, D, E, that's 5 letters. So our critical value for RS is 0.9. So therefore, to the smallest it can be to reject H0 is 0.9. And we know that n is 5, so that's 5 times by 5 squared minus 1. So obviously that's not too difficult to work out. We can rearrange that and get 6d squared, and that's is equal to 0.1 times by what these two multiply by, so that's 5 times by 24. So that gives us sigma d squared equals to 2, which is yeah, not too bad. So that's the smallest at d squared, which is the smallest that it can be in any circumstances, because that basically accounts for just two nearest to each other swapping over. That's the most. So you can't have you couldn't have something like this, A, B, E, D, C, because the E and C have swapped over and they're not close enough to each other. That would give a higher value for d squared. So in fact, the smallest the only way it can actually show that suggest positive association under the 1% one tail criteria is if d squared is 2, which effectively means that just two rankings are swapped over, two adjacent rankings are dropped over. Remember, sigma d squared can't be equal to 1, because if one swaps over, the other one will swap over. So therefore, I'm a little bit surprised at 3 marks for part C. I got a little bit put off by this, but maybe they were thinking of something else. Here they talked about deducing that sigma d squared is equal to 2. But to me, it seems fairly intuitive here. Any order where two adjacent ones are swapped over would be okay. So e.g. that, or you could have that, BA, you only have to give one of them, BACED, so long as two adjacent ones, because all of those would lead to a sigma d squared being equal to 2. Okay, so that's it for this video. I will in future videos tackle some of the later questions. Okay, so that now is question 4 and 5 done. I will do 6 and 7 in a separate one, and then the later ones also. Thank you, bye.